In the previous lesson, we saw how to construct class hierarchies, and specifically we saw how to create an algebraic data type consisting of a sealed abstract base class and some number of case classes that implement it. This wasn't too different from Java or C++, with the exception that when you seal an abstract base class, you can do exhaustive pattern matching, which was nice. Scala also provides another mechanism for composing class hierarchies, and this mechanism is called traits. Traits turn out to be much more powerful than abstract classes. So the place where I want to start exploring traits in this code is here. We've extended comparable, which is just java.lang.comparable. It's a Java interface. The interface specifies only one method, which is this compare_to method that we had to implement. And when we were using mass, we were able to say if have.compare_to need is less than 0. And this was sort of a clumsy way of trying to articulate, well, we need to go shopping if we have less of a certain ingredient than the amount that we need. It turns out that Scala provides a trait that does something similar, but in a much nicer way. So let's look at this. I'm going to open up the standard Scala doc for the ordered trait. So the first thing that we notice here is that the ordered trait extends the Java Lang comparable interface, which is what we've implemented already. This is handy because if you have an instance of ordered, you can pass that to anything that expects a Java Lang comparable polymorphically. But it does a little bit more than comparable does. Let's scroll down here. We can see that there's an abstract compare method. That's sort of like compare_to, although compare_to is made concrete here. But it also has a few other concrete methods. Less than or equal, greater, and greater than equal. One thing I haven't mentioned yet about the Scala language is that you can provide methods with symbolic names. You can say that this is maybe sort of like operator overloading in C++, but it's a little bit more flexible. Of course, if you're designing your own library, and you're considering using symbolic method names, you probably want to be pretty careful and use method names that make sense, otherwise you'll just confuse people. But in cases like this, it's pretty handy. So if we go back over to our code and we say that mass extends ordered, and we implement compare, then instead of saying this crazy thing, we can just say if the amount that we have is less than the amount that we need. We can save that, and this compiles just fine now. Well, that's a nice cleanup, but if ordered had just been an abstract base class, we could have done exactly the same thing. There was nothing special there. The thing that's special about traits is that we can mix many of them together, which is something that we can't do with multiple classes. You can't inherit from multiple classes. So let's see how this works. We previously left a little bit of a mess in our mass algebraic data type because we had a lot of copy and paste here for how toString is implemented. We can probably imagine that for any kind of unit of measure, the toString implementation is going to look pretty much the same. It'll be the amount followed by some symbol representing the unit. So let's define a trait called measured. The measured trait will have amount. That'll just come from mass. We'll pull that out in a moment. And it'll also have a symbol. That'll be our string. And the thing, again, that we want to factor out here, the thing we only want to have to write once, is the toString implementation. So let's do that. Okay. Again, this looks just like an abstract base class. But the part where it differs is that mass can extend both ordered and measured. The way that we do that is using with. Now, before I explain how exactly this works, let's just clean up our loose ends. Let's say amount was defined in the base, and we don't need toString anymore. Instead, we need symbol. Also, just to make the code a little bit more concise, I'm going to leave off the override and the type description here as well. Since this is an algebraic data type and everything is defined very close together, it's pretty readable if we leave this off. Okay, so not quite as much repetition here. Now let's explain how this is working. When we say that mass extends ordered with measured, or, if we wanted to, we could do it the opposite order. We could say measured with ordered. What the compiler will do for us is actually synthesize sort of an artificial base class consisting of all of the properties of measured and all of the properties of ordered. That's what it means when we say extends measured with ordered. I want to be clear about this because the syntax is a little bit confusing to some people. We're not saying that mass extends measured and then with ordered is some other thing. That's not the case. Measured with ordered is what's referred to in the language spec as a template. It's sort of the aggregate parent class, if you will. So the other question that this brings up is, well, this looks a lot like multiple inheritance. And the problem with multiple inheritance in C++, and if you've done any C++ programming, you know this pretty well already, is that if you inherit two concrete instances of the same thing, for example, let's say that we have a two-string method defined in our measured trait, and we also have a two-string method defined in, let's call this conflict. Well, the question with multiple inheritance is, if we inherit both of those concrete members, which one do we actually want to use? The way that Scala deals with this is that order matters. So if I say that mass extends ordered with measured with conflict, the order that these traits are mixed in determines the overriding behavior. So in this case, mass is going to extend conflict, which is going to extend measured, which is going to extend ordered. We're linearizing those traits when we compose our synthesized base class. So in this case, the conflict implementation will win. If we do it the other way around, ordered with conflict with measured, then it's like saying mass extends measured and measured extends conflict, even though conflict and measured haven't been declared as extending one another in any way. This is the way that the compiler will sort of linearize this class hierarchy for us. The actual linearization algorithm is a bit more complex than this, and rather powerful because we can have traits extending from other traits and so forth. As an example of that, we can say that mass, instead of being an abstract class, we can say that mass itself is a trait. Now, the thing that I should mention here, and this is something that actually the Scala community is really only just starting to learn about and understand, is that the compiler seems to compile a little bit slower when you're extending from a trait rather than an abstract base class. So build times will be a little bit slower, you might notice. The other thing that you'll notice is that your code might also run a little bit slower at runtime if you mix together a bunch of traits, because the code that the compiler generates involves a little bit of indirection. And with that caveat aside, traits are very powerful. You see them used all over the standard library, and we'll end up using them in our calculator code as well.